In this video, we will create a mesh based on the geometry of a counterflow plate heat exchanger, which we drew previously. We'll create a surface mesh, ensure our name selections were correctly imported, and generate the volume mesh for both the water and oil domains. Finally, we'll observe the generated mesh to ensure inflation layers have been added, and we'll review critical mesh statistics. If you launched Fluent Meshing directly from SpaceClaim, you should see the model in the display window. Otherwise, choose Watertight Geometry Workflow from this list, choose Import Geometry, find the file, and click Import Geometry. For this model, we will forego local sizing and instead apply a global element size range to the surface mesh. Ensure No is selected and click Update for Add Local Sizing. While editing the Create Surface Mesh task, we can see these red boxes on the surface of our bodies. These are indicative of the maximum and minimum element size from the menu on the left. Although it's difficult to see, there are in fact two sizes of boxes. Let's change the minimum size to 8 and the maximum to 25. Click Create Surface Mesh. We can already see here that our mesh size may be large. Because each subdomain of water and oil requires fine enough meshing, the overall mesh count may be in the hundreds of thousands. This will simply mean that the solution may take an appreciable amount of time to solve, but it would be quite difficult to generate a coarser mesh and still retain the relevant heat transfer effects. Under Describe Geometry, we will choose only fluid regions with no voids. Because we applied the shared topology when we modeled the geometry in SpaceClaim, we can leave the bottom option as No. If this was not done previously, we may have needed to do it here. Click Describe Geometry. Next, we can see all our name selections from SpaceClaim. If we chose not to create them in SpaceClaim, we would have had to sort through each component and individually decided which default name applied to which boundary. Let's quickly double check the correct boundary type has been applied. We have our intermediate walls, oil side walls, and water side walls all correctly set as wall. Our oil inlet and water inlet we need to change to mass flow inlets. And finally, our two outlets were correctly imported as pressure outlets. If we need to, we can update these options later in the solver setup. Click Update Boundaries. Next, we see that Fluent imported each of our components and applied a fluid type to each. If needed, we can manually select the region type from this menu. Finally, we'll create the volume mesh. We'll retain the polyhedra option with its default values, but we'll switch from 3 to 4 inflation layers. It may take a minute to generate the volume mesh. Change the clipping plane from Y to X so we can better see the inside. If we zoom in on one of the plates, we can see the 4 boundary layers applied to each of the walls, with the polyhedra in the interior. Disable the clipping plane, and right-click one of the surfaces. The surface is highlighted, and its name is printed to the console. We are double-checking that the inflation layers were applied to the correct surfaces. As this is an inlet, this is correct. Right-click the surface again to deselect it. Before we save and export our mesh, we need to check some critical statistics. In the console window, we can see the total cell count of being just over 340,000. We see our maximum skewness as just over 0.6, and our minimum orthogonal quality of 0.37. Finally, let's save our mesh. Go File, Write, and Mesh. The default name is the same as the geometry name. At this point, we're ready to set up the solver. Click Switch to Solution. This concludes our video on the meshing of a plate heat exchanger. In the next video, we will choose the solver setup options using Ansys Fluent. Thank you for watching.